Hello, everyone. I'm David Keenan. I am manager of the Language Runtimes and Performance Group at Twitter. I'll tell you a little bit about my background. I've worked at Twitter now for a little more than 2 months. Before that, I was a performance architect for the Java platform at Oracle. And before that at Sun. Did that for just about 8 years. And been dabbling in performance of the Java runtimes and Java languages and Java on the runtime since '98. So I'm going to, usually I've done a series of these talks around advanced JVM performance at Java 1. And a lot of times I try to give some insight as far as where the optimizations are going for the JVM. This time I'm not going to be able to do that too much. I will try to hint where I think things should be going and potentially are going. I'll kind of give it a Twitter spin for this one. Okay, let me just get control. Okay. Okay, sorry, I did not have control of my slides there for a second. Now I do. Okay, so the first section is just a general overview of what is performance tuning and what is performance analysis. What are the steps to take? I'm going to start off with a top-down analysis approach. Now, top-down performance analysis typically happens, and it's actually the first thing you should consider. When you have control of the highest level of the stack, when you can change the code at the highest level of the stack, you should take a top-down analysis approach first. Basically, this is monitoring your target application under load. You take a look at system-level diagnostics such as VMstat, MPstat, the simple tools that are available on your operating system. Basically, give you an idea if you're churning user space CPU, whether it's you're spending a lot of time in the kernel, disk I/O, and such. That will give you an idea where to go, and sometimes it will point you to the JVM. JVM-level diagnostics are mostly garbage collection logs. And that's really the most common place you'll see a performance issue with Java. So you want to take a look there and see if you can rule out or at least point to garbage collection as your initial problem. Finally, if you don't see GC as blaringly obviously wrong or spending a lot of time there, you want to profile your application under load. So there's many profiling tools out there. The idea is to give an idea of what aspects of it, what parts of your Java code you're spending a lot of time in. So once you're able to identify that piece of code, you take a look at it, you try to analyze where it's spending time, make modifications to make the code more efficient from a runtime perspective, but most importantly, try to reduce allocations that are spurious and unnecessary. If you're able to control the rate of allocation or limit allocation at the application level, you're reducing pressure on the garbage collector, and you're reducing pressure on all other aspects of memory management in the VM itself. So frankly, that is your biggest thing you can do as an application developer, is try to limit the rate of allocation. Now, that being said, there's obviously gotchas there, and there's been a lot of talk of how to do that. I'm not going to really be terribly specific. Pooling can be bad. So be careful in that regard, but there's obviously ways to reduce, how much you're allocating, and you should consider that when you find a method that is showing up in your profile and you see allocation in a loop, that might be the problem. Right? That's basically where I'm getting at. And then repeat, right? It's a cycle. It's not a one-time pass. Every time you go through this cycle, you should expect to see some performance improvement. Sometimes not, but you have to keep going back and trying. Second general approach is a bottom-up analysis approach. You go down this path when you don't have control of the upper layers of the stack. This is really the approach that's taken most often when you're doing JVM and OS performance optimization. So if you're trying to optimize for the JVM, you will take a bottom-up approach to understand what's happening at the lowest levels of the stack and how you can influence that. So the first step is to monitor CPU level statistics against the target application under load. This is using hardware counters, things such as cache misses. You're trying to track cache misses, path length, branch prediction issues, things like that. Then the next step would be to use profiling tools that can give you that level of observability down to at the hardware counter level. For instance, there's, I've spent many years using what is now Oracle's Studio Performance Analyzer, but there are other tools that do the same level of introspection. Intel's vTune, for instance, is another one. But the ability to track at CPU cache misses and point to the upper levels of the stack that are causing you a problem, that's the tool you want to use. Now, in this approach, you're not looking for the Java code because there's not much you can do at the Java level to really manipulate cache misses. Okay, if you're, walking a data structure a lot, maybe. But it often is the internals of that code that's the problem. So the next step is to look at the generated assembler. What is the hardware instructions that are issued based on the Java code that you've written? And then that's where magic comes into play. You have to understand what x86 is, or what Spark, or whatever the target assembler language that you're looking at, and try to understand how that code is generated and what optimizations may or may not be missed. This is where that level of experience comes into play. Next step would be manipulate your Java C or Scala compilers. Those that are manipulating the bytecode. Sometimes you can go one step higher than that and look at the common language libraries that you're using, whether it be the core libraries in the JDK or your own internal stuff. Typically, anything higher than that, you're not going to really impact from a bottom-up analysis. It's actually, as you go further down this list, it's diminishing return from this approach. So again, as I started off in this discussion initially with a top-down analysis, that is, for those in this room, those that are dealing with Java code, top-down is the way to go, and bottom-up is just so you can understand what the other aspect of the way of doing things. Okay. The performance triangle. Latency, throughput, and memory footprint are very delicately tied together. And in many ways, we want to be able to either increase throughput and reduce latency, or keep a hold on memory footprint all at the same time. Unless you're doing drastic manipulation of either parts of that points in the triangle that impact that behavior, you're not going to be able to do that. For instance, if you want to improve throughput, the only way you're going to do that without impacting the other two points of the triangle is to have a faster CPU, or have a faster compiler, something that does drastic changes that impacts the efficiency of your code. But typically, if you want to reduce latency, memory footprint goes up. Right, the tried and true way of reducing latency in Java applications now is to have a very, very large heap, and really avoiding garbage collection, and promotion in general. But I'll go further into that in other slides. So as you can see in this, footprint gets bigger, latency gets smaller, throughput actually got smaller too. If you wanted to increase throughput, you're increasing everything, more or less. In order to increase throughput, where you're really really looking at the amount of time, the amount of work you're doing, you're trying to optimize the amount of work over time. And when you do that in tuning in Java, you're ignoring latency. In that regard, it's going to get bigger. And you often have to have a very large heap to avoid garbage collection as well. So increasing throughput right now is really, you're increasing all aspects of the triangle. Same thing with smaller footprint. If you want a smaller footprint, latency is going to go up, right? It's the inverse of the two. The way we assure lower latency in Java now is to have a large heap. So if you're trying to limit the size of the heap, you have to keep a close eye on latency. Same thing with throughput as well. It's the classic trade-off. Okay. Next section is performance metrics. So metrics are important. You have to choose the right metric, in order to actually achieve the goal that you're trying to go after. And identifying metrics is tricky business. You want to make sure that the metric that you identify tracks what's important to your user. Also, if efficiency is important to you, you want a metric that tracks that for your company, and what influences your bottom line, and what are you willing to trade off? As I mentioned in the previous section, the performance triangle, there is trade-offs. You have to have a realistic approach, to this. Define success well is important as well. As I said, the processes for performance analysis or improving your application is a cycle. So if you don't define what success is, you're not going to be finished. You can always keep going after it. General rule of thumb is, it's not broken, don't try to fix it, because there's other problems you can go after. And perfect is the enemy of done. So you have to, defining success is very important. Everybody wants it all, right? We want high throughput, fast response times, and a small footprint, but that's not free. It's just the reality as you go after the metrics that you're trying to track. Make sure that the metrics that are targeting what your customers are looking for, and use statistical analysis when looking at those metrics, because metrics with high rates of variability can be useless in some situations. A good example is average response time, which I'm not really a big fan of, as you'll see. High rates of variability in average response, you basically don't see rates of variability in average response time. You're just looking at what happened at the end. You can have very large outliers, and you can have, you don't know the shape of the data, your data at all. So it's important to, in that situation, you should use statistics. Okay, throughput metrics. The most common one is transactions per second. Also known as pages per second, queries per second, hits per second. And it is a good measure of top-line performance. It is as far as, and also an efficiency metric as well. And I've listed average response time here as a throughput metric because in many ways it is. It is the inverse of transaction per second. It's time over the number of transactions. Sometimes it's useful as a rolling average. But often it's, the common mistake I see is seeing response time and CPU utilization as the common, your primary metrics for tracking performance and regressions. And it's a good way of holding the line on efficiency. But a good example of where those two metrics fall apart is, say you were trying to reduce response times by doing concurrent garbage collection. What would happen? Right? Your response times would go down, but your CPU utilization would go up because you're doing GC work concurrently. That seems like it would deliver something good to your customers. However, it would be marked as a regression if you tracked average response time and CPU utilization. So keep that in mind. Okay, and lastly, so CPU utilization is a good use of a good metric for computational efficiency. It is not something you should ignore, but you should take it into consideration with other optimizations. It is good for capacity planning, but as I said, it's not good for development regression testing. Latency metrics. I've kind of listed it in the ones in order of popularity for myself. So maximum response time is something that you always should have an understanding what the worst case for your customers are. It doesn't have to be a primary metric that you're tracking your goals against, but you should have an understanding of when it falls over completely. 99th response time drops the most egregious outliers and will give you a bit more consistency in the metric itself, less variability. Maximum response time is, is always your worst case. So it can be highly variable depending on the rate of garbage collection, the state of the application, and so on. So 99th percentile is that would be my suggested metric for tracking response time. 90th percentile response time does fairly well. It can give you a false sense of security, though. In those situations where you have many young garbage collections that are that are performing very well, and a few very large full GCs, 90th percentile response time may miss it completely. So any one of these top three metrics, you should be in combination with the first one in combination with the next two to give you a full picture. I'm mentioning critical injection rate here as a new way of kind of looking at response time, and it's an example of it is critical JOPS in Spec JVM 2013. What that is it's the achievable throughput under an SLA response time restriction. So it's the notion of, what is the throughput I can achieve if I can't have, if my 99th% response time is less than 50 milliseconds. That's a pretty handy tool for sizing for what you're looking for your customers. It is in Spec JVM 2013. It's a composite of several response times, but there's a lot of data there. So, and don't use average response time. It really is not a latency metric. Please just don't fool yourself. It's been used for many years, and I think it's impacted how. Frankly, I can say frankly, it's impacted how JVM optimizations have happened over the years. We're in a situation now where we don't optimize well for low latency because of average response time being so important for such a long time. So change that. Memory footprint metrics. The best memory footprint metric for Java applications is the heap size after a full GC, the live data size. Many times you don't end up seeing that, but I'll list it in an upcoming slide how to find that. Native process size, this is the way I do it on my Mac and on Linux. It gives you a good idea of what the reserve memory size is, PS, AUX, in the PID. And lastly, static footprint. So why does static footprint matter? Well, it probably doesn't matter to a lot of enterprise application developers. However, if your application needs to be downloaded by a client over a network, it's going to matter, right? So having an understanding of how large your jar is in that situation and what level of compression you're using is important. Okay, I'll try to. Okay, now these next slides, I will try to give as much detail as I can, but frankly, it's a bunch of garbage collection logs. I'm going to point to one value. There's tooling in development by Twitter and other companies to make this a bit more easy to understand, and Oracle does have tools that they have available as well. But this is the tried and true way that's common to everybody. So you can do this just by doing verbose GC or print GC details and such. So I will try to give that, but I apologize if it's confusing and the slides will be posted. I'll put them on slides on SlideShare myself as well. So for review later. Okay. So as I mentioned, the first one is calculating live data size. And essentially, you want to track the size of the old generation after full GCs. And I've highlighted the last one in blue is being the size of the heap after a full GC, 798K. Next way of looking at calculating live data size is tracking the size of the old generation after young GCs in the event that no full GCs occur. I mean, if we're tuning our applications well, we should avoid the full GCs. In this case, you're trying to track and see what the rate of change is. And if you look at those three values that I've highlighted in blue there, you can see that it's increasing. So promotion is happening. The old generation is getting bigger, so albeit slowly. Okay, so the next basic step for JVM tuning is sizing the old generation. A good starting point for sizing the old generation is 2 times the live data size at steady state. So, this is a general recommendation of a starting point. I say 2 times because you need to have at least the size of your live data size. And if you size it too closely, you're at risk for, depending on the garbage collector, but you're basically at risk for promotion failures, not having enough space in the old generation to promote your transient objects from the young generation. If that happens, you full GC. So you should have enough padding there. If object promotion rate causes frequent CMS cycles and gets to the point where you're concerned about concurrent mode failure or promotion failures with CMS, both of those cases cause full GCs, then padding it a little larger is going to be important. So what you need is a notion of promotion rate, which I'll highlight next, coming slides. So in the case of your live data size being 5 gigabytes, your starting point should be 10 gigabytes. That's the old generation size alone, not the overall heap size. So basically, if you're just setting MS and MX, ignoring the size of young generation. 10 gig is a good starting point, but really it involves the size of young generation as well, and I'll highlight that coming up. So it's important to size the old generation because you don't want full GC pauses unnecessarily. And if you don't size them the same, XMS and XMX the same, the only way you grow the old generation is via full GC. So when you're running an enterprise application in production, it's, unless you're trying to overcommit memory on a system, I see no other reason to set these values different. So sizing the young generation is so a good starting point for general recommendation for looking at throughput and latency is to size the young generation to be equal to the old generation. It used to be that we'd have it smaller, but allocation rates and the speed of these processors that we have these days really kind of merit having that much space in the young generation for allocation. You want to increase the size of the young generation if you have a higher allocation rate. In many cases, young generations are 2 to 3 times larger than the old generation. In some cases, a lot bigger than that. Now, don't be afraid to set it large because GC times are dominated by copying to the survivor races, not necessarily, not the size of the young generation. It's just the size of the live objects. So if you size a young generation so most objects die in the young generation, you're going to have fast young GC pauses. And general rule of thumb, higher allocation rate, larger young generation. So an overall example of an enterprise application covering the last 2 slides. Say you had in-memory cache of 3.5 gigabytes, your overall live data size was 4 gigabytes. You have a high allocation rate in transient data, but you do know that most objects die in the young generation. Then it's the general recommendation. You want your young generation to be equal to the old generation. And that's what this set of tuning does. The overall heap is 16 gigs, and you're specifying the young generation to be 8 gigs. Minus XMN is the same as new size and max new size together. So we're fixing the young generation size at 8 gigabytes, and then the remaining is the old generation, and that is 8 gigabytes as well.
Would you ever make it larger?
Which one?
Young.
What, I'm sorry?
Would you make the young larger?
Oh, absolutely. Yeah, I'll go into that. Yeah.
Is there a chance that because your young generation is so large, and can you size it too big so that it's not running young GC enough, and you have probably objects there, or is it always going to run frequently enough so that there won't be any long problem?
Okay, let me answer that question further on in the presentation. So that question was, is there ever a situation where the young generation could be sized too large where it would impact death rate of objects, right? Okay, so we'll talk about that later. And your question was, would you ever increase the size of the young generation beyond the size of the old generation? And yes, to that as well, and we're going to go right into that. Okay, so basically, you'll see the sections that I have coming up are tuning for throughput, tuning for latency, and tuning for footprint. So we'll go through specific aspects of it there. And I'm going to try to go a little quicker through there so we have more time for questions, because I think we'll have a good amount of them. Okay, so the next step is choosing your garbage collector, right? So for throughput, general rule of thumb, use parallel old GC. It is the quickest throughput collector because it's not trying to do anything concurrent. Simple as that. Low server response times, you want CMS as is the older technology. It's kind of tried and true. The problem is that it can be very highly tuned to your allocation rate and your promotion rate. But if that changes, it's a pretty steep cliff. So it's pretty brittle. G1 is the current development focus. If you can tune G1 very easily to get very close to CMS pause times. However, it is slightly faster because it has to deal with remember sets and there's more work involved with rate barrier. But there's more work involved in the aspect of doing a young GC collection for G1 because it's trying to keep an eye on concurrency and what it can do, what work it can do concurrently. That being said, it's pretty darn close. So my preference today is to use G1 GC. Mainly because it's not nearly as brittle as CMS. So keep that in mind. I mean, if you're trying to optimize the last 2% out of your response time, you're probably stuck with CMS. But if you're really kind of concerned about efficiency of development and not having things fall out on its face in production, G1 might be a better choice in that regard. Okay. General recommended GC tuning, GC logging flags. So these are the ones that we generally recommend. Print GC details and print GC timestamps are the tried and true ones that everyone should be using. And log GC to a file also is good as well. So it doesn't, it's not going to standard out or standard error and screwing up your logs. So the rest are just various levels of information. I like print heap at GC. It gives me an idea of what's going on with the spaces. Like it gives you the size of the survivor spaces. Tenuring and distribution is very important as well. You should, and if you're able to, well, actually, I'm just going to say at this point, with these flags, if you take a look at the Java Performance book by Charlie Hunt, a colleague of mine in the past, goes through this in great detail. So I would highly suggest that book. Okay, so this is calculating allocation rate. As I mentioned before, having an understanding what your allocation rate is going to be important. So basically, it's the rate of the, if you look in red, it seems to be coming out okay. From here, I can't really tell very well. But the value listed in red is the size of the young generation before the garbage collection, and the value listed in blue is the size of the young generation after that garbage collection. And the two yellow values is the change in time during between those 2 points in time. Well, it's the time spent between the garbage collection events, and that boils down to an allocation rate of 62 megabytes a second for this application. So that is allocation rate. Next is promotion rate. So this is essentially changing. It's tracking the changes in the size of the old generation and over time. And the sizes of the old generation are listed in blue. And this application is actually rather tuned well, and it's only promoting 6 kilobytes, 6K of data, a little more than 6K of data a second. Okay, now we're going to just jump right into tuning for latency. And I'm going to start off with CMS. Okay, so enable CMS, there's the CMS flag. Some good flags to have for CMS is CMS scavenge before remark. So this will do a young generation scavenge before a remark phase. Reduces the work of what needs to be remarked greatly, highly suggested. Parallel reference processing enabled. Used to be, well, yeah, I'm assuming these two flags will be default for CMS if CMS was more of a development target, but I would suggest investigating these two flags. The last is initiating occupancy fraction. 70 is actually a very good default, and that's what it is. If pushing it up further basically means that you want CMS to act more like a throughput collector. You're saying you don't have to start your concurrent. This basically says what is the fraction of the heap to start concurrent activity. So if you push it up, it will start doing concurrent work for old generation collection later. If you push it down, it'll do it earlier. So if you see concurrent mode failures and you're running CMS, turning this down is a good idea. You're giving your CMS more time to do the concurrent work that it needs to do. A lot of the phases are not parallel in CMS, so it has the notion of the CMS threads getting behind and not being able to keep up with the allocation rate can happen. And this is the knob that you tune to manipulate that. Basic tuning guidelines, size of permgen, I'm going to mention that a few times. I would set the old generation size to be 2 times the size of the lab data size and start off with the young generation size equal to the old generation size as before. Increasing young generation size, you do that to handle higher allocation rates. And increasing young generation size if you see promotion rates being high. This is kind of an inverse way of looking at things than others. This is different. This is how we do it at Twitter, and that's why I'm mentioning it here. Mainly because memory is on the table in our configurations for our low latency applications. So you'll see in the examples that I give that some of them have rather large heaps. Sometimes, actually, a more traditional approach for tuning of CMS is to limit the size of the young generation, to have lower young generation pauses. So, it can go either way. So the size of the young generation can influence the rate of or the length of the pauses for the young GC pauses. But when you're able to control the rate of injection for your application, the allocation rate, and the promotion rate, then you tune it up. So increasing the size of the young generation. So if it suffers premature promotion, Yeah, okay. You're going to increase the size of the young generation to basically alleviate premature promotion. Premature promotion is the notion of GC is happening too often and my objects are not dying young. They're not dying in the young generation. And if they just had a bit more time, they'd be able to die. So the way you influence that is by making a larger young generation. It also, so essentially that, it decreases the rate of GC and gives more time to die. You want to increase old generation size if promotion rate is too high. So you'll see concurrent mode failures, which invokes a full GC, if you don't have enough space in the old generation and the CMS threads are not able to keep up. So increasing the size of old generation is going to be important there. Okay. Tuning for latency. This is an example of a pretty well-tuned CMS application. You notice I have CMS scavenge before remark on the second line. On the fifth line, I have CMS occupancy fraction. It's set to 70. I believe that is the default now, though, but I'm pulling it from an older log. I'm also manipulating the survivor spaces in this case because I'm trying to tailor the activity of the young generation to the promotion rate. To the allocation rate that I have. And the big takeaways with this is the survivor ratio tuning and the size of the young gen. Do we have one question for this slide?
Yeah, just you're doing something I encounter a lot with some of the CMS initiating occupancy fraction, but you don't have the corresponding flag to set that only. So doesn't that only take effect the first time, the first pass?
So in later versions of the JDK, I'm fairly certain that changed, and the only notion is gone away. But I will look into that. I don't think that's the case because it's we see pretty big impact by manipulating this flag throughout the course of the application. So yeah, I don't think only is part of that anymore, but I could be wrong. That's probably worth looking into. Yes. Oh, what is high? I mean, obviously, I think it's. So the question was, what is a high promotion rate and what is a high allocation rate? A high allocation rate is essentially if you're seeing, well, if you see premature promotion. So it's directly related to the size of your spaces, how big you can be. As far as allocation rate is concerned. The biggest knob you have to manipulate allocation rate is your application. So if you're seeing premature promotions, you need a longer young generation. And the reason why you're seeing those premature promotions probably is because your allocation rate is high. So what you'd see is your young generation growing. I'm sorry, your old generation size growing until it had to full GC or CMS cycles ensued. So tuning G1 for latency, I'm not giving a lot of detail here, mainly because I have not investigated it to the point where I can give equivalent CMS flags. Like tuning it the way we do at Twitter, kind of looking at when we have promotion rates and allocation rates under control. I don't have the equivalent flag set for G1 just yet. So I'm going to give you an idea of what I will look at and the general approach for G1. G1, it should be much simpler to tune. Essentially you want to start with really just setting the max GC pause. Max GC pause in G1, I'm sorry, also the overall heap size. You'll set the equivalent heap size that you're running with CMS to start with. But I would not set the young generation size. I wouldn't start with messing with survivor ratios off the bat. The way that G1 tries to target its pause time, the way it tries to achieve its pause time target is greatly by manipulating the size in the young generation and the aspects within it. So if you fix it, it kind of short circuits its adaptiveness. Right. So again, one last notion for G1. I mean, you would go after if you get to the point where you see it's not keeping up with your rate of allocation. Yes, increasing the size of young generation makes sense as the next step, but don't do that first. As you look at G1 output logs, you'll see how much time is spent copying, how much time is spent with remember sets, And you want to tune it to keep remember set processing and the time spent manipulating remember sets low. You want to see most of the time spent copying. Tuning to consider for G1. Initiating heat occupancy percent. This is same as CMS, essentially. Max GC live threshold percent is the amount of live objects in the old generation before a mixed collection occurs. This gives you an idea. This knob allows you to manipulate whether you're going to be more throughput mode or more concurrent mode for G1. Heap waste percent is really how much fragmentation can you tolerate in the heap, how much lost space. And mixed GC count target is really what is. It's how it divides up its concurrent work, and that's one of the thresholds that tells it how much concurrent work you're allowing it to do. Actually, the last three are all the same type of activity. If you take a look at that InfoQ article by Monica Beckwith, she presented a couple talks on G1 here at Java 1. That's an excellent article to kind of jumpstart you looking at G1 for tuning. Okay, so here's a sample set of tuning that really is where I'm at with looking at G1. I enabled tier compilation and increased the code cache sizes because that's important when you use tiered compilation. That's pretty much it. You see, I'm just setting the target, the occupancy, and just using G1. Okay, tuning for throughput. Parallel GC. It's the most efficient collector for throughput. And if you're trying to avoid garbage collection, there's a lot of garbage collection schemes that can happen. I would start with this one as well because it can be more. It is the most efficient garbage collection. It's just not trying to do anything concurrent. Old generation needs to be 2 to 4 times the size of live data size. Mainly because even though it's a parallel old generation collection, it's still pretty darn slow. So you want to kind of avoid that and give space, not to have a full GC. Young generation is usually 3/4 the size of the heap. Often used with aggressive tuning, aggressive ops, and tier compilation. And disabling adaptive sizing and tuning as survivor spaces directly is really, that's when when you're going after the last 5 to 10% of tuning, really 5% of tuning, that's where you start to manipulate those flags. Here's an example of a tuning set with parallel GC. Notice the size of the young generation is 27 gigabytes, and the size of the heap is 29. So that's pretty heavily tuned for competitive benchmarking, actually. I really wouldn't use that in production, but this is actually a tuning set for JVM 2013. Okay, G1 for throughput. G1 for throughput right now is actually, you can tune G1 very similarly to parallel GC to get pretty equivalent behavior. Again, G1 still tries to do some concurrent work, and the overhead of a young generation is slower. It is slower than parallel old. However, the tuning is similar. And one of the approaches, I can envision with G1 that there would be a throughput mode for G1 eventually, and a concurrent, low pause mode for G1. Okay, we got a question up here?
Yeah, but considering the fact that aggressive ops does nothing.
Aggressive ops does nothing. You're right, but the reason why it's in there is that it makes it a little more portable if you're using older versions of JDK7 and newer versions of JDK7. That's why I still have it in there. It also does. What does it do now? No, it does nothing. You're right. Yeah. Yeah.
I'm just quoting you.
Oh, before. Okay. Yeah. You asked me a question. Yeah. It stopped. It really. When we moved from JDK6 to JDK7, it did a few things, and as we've gone through the updates in JDK7, at this point in JDK40, it's doing nothing at all. I could be corrected. In might be some corner cases they've added since I've left, but yeah. Notice the initial code cache size and the reserved code cache size in this situation. If you're using tier compilation, which I do suggest that you do, it has a lot of potential to be faster than just C2 alone. But you got to increase the size of the code cache to, otherwise it fills up, stops compiling, and then you'll be, why is everything so slow? Yeah. Here's an example. Okay, tuning. I labeled this long slide. This is the same. Did I do the same thing again? Sorry. Oh, okay. I'm sorry. I'm confusing myself. Tuning CMS for throughput. You're basically configuring it to avoid promotion. You want to, so as I said, CMS is rather brittle. So if you're really going to go after CMS for throughput, you're basically going to tune it to have very large young generations. And you're also going to need to control your application to limit promotion and kind of clamp down allocation rate. Clamping down allocation rate enough that you don't have premature promotions within CMS. So separation, having an application design that separates stateful and stateless will allow you to, those stateless applications, you can target those more to fit within CMS. Young generation should be big, just like with parallel old. Very large heaps, very, very large old generations. You're basically using memory to avoid full GCs. You can tune the survivor spaces manually to make sure that you're not promoting unnecessarily. And here's an example set of tuning CMS. Okay, there's a typo. In new size and max new size, they should be both 16, not 19 and 16. I'll fix that before I put it on SlideShare. So that would, in this tune situation, considering that the new size should be 16, there would be only 2 gigs available for the old generation. So that's the steep cliff. If you cannot promote into the old generation, it's a full GC. And if you do end up doing concurrent activity, if you lose the race, that's a concurrent mode failure. So it's a very steep cliff with CMS. Tuning for footprint. Now, this stuff, going down this path is relatively new. I don't have a lot of experience targeting tuning for footprint. The general methodologies are pretty well known. We can't tune for footprint until we are able to use the garbage collector to ensure that we have low latency. We're not there yet. So once the garbage collector once we can tell the garbage collector that my max pause is 10 milliseconds, or my max pause is 50 milliseconds, and it actually achieves that, we're not going to be able to trade off CPU for footprint, right? So right now it's a rather difficult thing to wrap your mind around in being successful. But in many cases, if you're copying your tuning parameters from one application to the next, there might be cases where you can reduce the size of the heaps that you're using. So old generation also still needs to, you still have to have enough space in the old generation. So two times the live data size. Start off with young generation to be half the size of the old generation. So notice that I had it be equal before in previous configurations. It's half this time because we're trading off more frequent young garbage collections for reduced footprint. The strategy is to reduce young and old GCs independently until the maximum acceptable end user response time is met. So you have to in order to go down this path as well, you have to be tracking what's important to your end users, the response times, very, very closely. If you're using parallel, it's definitely not low pause. You're basically trading higher response times for lower footprint and lower throughput. So you're not never going to achieve low pause and reducing footprint with parallel. Here's an example of the flags for this configuration. I got a typo there too. Geez, I'm doing great. These two are supposed to be switched. Can you see that? No.
Which two?
MS and MX. I'm sorry, MX and MN should be switched. MX should be 8, MN should be 4. I'm trying to make the young generation half the size of the old generation. Okay. Footprint for G1. So heap in this case is going to be 3 times the size of the live data size, mainly because we're not going to try to tune the young generation. You want to allow G1 to adapt, and kind of settle on what's the best young generation size. Increase the pause target will decrease GC overhead and make you a bit more successful in that regard. Obviously, it's the same strategy. You're trying to reduce the heap sizes and keep them down while you're maintaining your response time. So it's going to be a balance between decreasing your heap size and setting your max GC pause millis to something that you think is appropriate. But if it's if you're really if 500 milliseconds is where you don't want it to go above, don't set it at 100 milliseconds and try to go after reducing the heap size. You got to be reasonable, and because G1, its heuristics are still in flux, and it's still trying to settle on what's the best policies, and the edges are a little rough still. So if you're trying to go after low pauses, it's hit or miss. So the larger pauses you're going to have more success with. We had a question over here.
So how are we reducing the memory footprint by setting the heap size big, like 3 times?
Right. Well, the recommendation before was to set it 2 times, but then also set the young generation as well, which means and when you do that, it's not. When you differentiate the sizes in the young generation, the calculation ends up being a larger heap, right? You're trying to. I'm setting this here 3 times the live data size and not allocating any space for the young generation. So the overall heap will just be 3 times the size of the live data size. Right? If you take, I can. Well, I'll just jump back quick. But in this case, I'm saying to be 2 times the size of the last data size, but then the overall heap, the young generation needs to be half the size of that heap, right? So it's bigger. So if your live data size is 2 gigabytes in this situation, right? So, yeah, it's actually the same. Ends up settling at the same size. You just a different tuning. Here's an example of that in G1. Notice the just sheer amount of flags necessary for G1. Once we're successful with that, it's going to be rather enlightening to not have to deal with so many flags. Okay, moving to CMS. Parallel new and concurrent mark sweep are required flags. 2 times the live data size, but the young generation should be half the size of the old generation. All right, so in the case of a 2 gigabyte live data set, your old generation needs to be 4 gigabytes and your young generation needs to be 2 gigabytes. So your overall heap size is 6 gigabytes with the young generation of, did I do that right? Yeah, 2 gigabytes. Promotion rate needs to be low enough so CMS concurrent mode failures, don't happen and you don't lose the raise. So that's where, application level code changes. If you're really going to go after lower footprint and maintaining response time, CMS really does require that you have a handle on your allocation rate and your promotion rate. So that's going to be important. Strategy is the same as with parallel GC, is to reduce the young and old GCs independently until a maximal acceptable response time is met. Tune the young generation first, then the old generation for CMS. It avoids chasing your tail a bit because the ratios change as you change the size of the old generation. All right, here's an example of that tuning. The reason why I listed survivor ratio tuning here for CMS, and I listed it in every case for CMS, is that it's one of the knobs that you can manipulate how allocations are handled. So it's something to look at. Okay. All right, we're doing pretty good on time here. I think I'll leave at least 5 minutes for questions at the end. Common performance tuning, performance issues. Okay, size of permgen. I see this an awful lot in enterprise application development. Sure, it goes away in Java 8, but who's moving to Java 8 anytime? Well, nobody is. But when it comes out, it takes a while to get there, right? So, the key thing to remember is permgen only collects when it's only collected at a full GC. So if your permgen is not sized well for your application, you're going to just invoke full GCs unnecessarily. And it's never, if you can see right here in this example, the last blue line, that permgen is just scraping. It's actually, in this case, it's larger than what the size, what's used is 1 kilobit away from, a kilobyte away from the overall size, right? It's not, so what happens here is an allocation in the permgen happens. It could be anonymous classes, and things with, it's most likely like JS, anything that populates the permanent generation. I'm not going to give my example because I think it's a little too confusing, but and essentially, if you get to the point where you're scraping up the size, up to the maximum size for the permanent generation, and if it is indeed full, you're not clearing space. So you actually get into this cycle of full GC after full GC after full GC. So it's real important to keep an eye on that. And you can see it. I mean, if you're using CMS, there's outputs, tells you when it happened. If you do one of the previous flags that I mentioned for garbage collection, which gives the reason, the cause, GC cause, it will tell you that it's perm gen collection, at least in later versions of JDK 7. So the recommendation I have for enterprise application is just size it big. I'd rather see you size it big and then see that you have extra space and then reduce it than to have the full GCs in production. It's just not worth it. It's really not worth it. I think 256 megabyte is big. The largest I've seen the perm gen need to be configured is 512 megabytes, and that was really a special case. 256 should be well beyond what you need, in my opinion. That's kind of where you want it to be. You just don't want to run into that. If there's a lot of churn, a lot of change in your application, and there's a lot of development that happens that goes into production quickly, tracking the total perm gen and the used perm gen, and kind of give an idea and flagging, maybe give yourself a warning when you get close, would be a good idea. Size of code cache. Typically, unless you're running tier compilation, it ends up not being too much of an issue. However, if you're going to run tier compilation, and I do suggest it, frankly, because it'll help applications start up pretty significantly. And essentially what it is, it's running the interpreter and then running C1, the client compiler, instrumented, instruments its code, and then you get better information for the server compiler. So you have the ability to actually generate better server compiled code if you use tier compilation. The scrubbing of the code cache it needs work, basically because the code for C1 and C2 are in the same cache now. You're doubling the size and it's running out of space. They are working on that. I believe there is a solution now. I don't know if it's been released. I don't think it has. But the way you do that, you get around it, is just tune it up. So that's that. I'm sorry, what's the question? See, in older versions of the JDK, the common sign, this is the problem, is that you'd see compiled failed if you did print compilation. So print compilation, you would see compiled failed. In Java 7, there was a sweeper, a cleaning thread, a way of cleaning the code cache. The problem is that what happens is you have to profile your application, and you'll see the interpreter consuming higher levels of the application in the profile, and it would be strange. You'll see it right away. The interpreter lights up, and the reason is that the sweeper, as it stands now, starts kicking out any code. Sometimes it kicks out code that it has to recompile, so it goes back, interprets, and it gets in a cycle loop. Right? There used to be very rare now, but several years ago, if there was a bad compile or you got in a compilation loop, where it would try to compile and then it had to decompile, it ran into a problem and tried it all over again, you'd see the same level of higher interpreter rate. That's temporary, right? I mean, and avoidable completely if you have the code cache size high enough. But they'll fix it. It's really a sweeping problem, and it just needs a better algorithm. Okay, so OpenJDK development at Twitter. So I'm going to try to go quickly through this so we have a couple of minutes for questions. Okay, so Twitter runs Java and Scala on HotSpot. Why HotSpot? Because it's the most highly optimized managed runtime for any language at this point, frankly. It's open source. And we were able to realize massive performance gain moving to HotSpot from other technologies. We own and optimize our platform. We build out our own diagnostic tools. We build, test, and deploy OpenJDK directly. And we optimize HotSpot runtime compilers for Scala and other implementations. And we are working on a tailored GC for Twitter's needs specifically. Our latency requirements are extremely low. We want a maximum response time, maximum latency, maximum end user response time of 10 milliseconds. which requires a bit of creativity right now to achieve. Our goals is to contribute back all of our work to the community. We are working closely with Oracle Java development. We're collaborating through OpenJDK, and we'll post our stuff on GitHub too. I mean, Twitter really, what we do to deliver our service to the public, we want to make public to you. I mean, there's really no restrictions as far as we're concerned. We're really just ramping up now. We've made some pretty key hires over the last couple of months. Pretty soon you'll be able to follow us at Twitter JDK. So that's new. I just kind of came up with that and haven't set it up yet. So in the meantime, follow me at Dags Keenan, and I'll let you know. Or you see down in the footer, Twitter Eng. If you follow that username, you'll see everything that we're doing as well. Okay. So thank you very much. I can ask questions, answer questions. Okay, up front. Yeah, so the question is, what is the recommendation for books for JVM tuning? The best book to really, the most modern, the most complete one is Charlie Hunt's Java Performance Tuning book. I mean, it's specific to HotSpot. It gives you, but it also tries to give you the fundamentals of tuning in of itself. You'll notice, I mean, I worked with Charlie, on some of the content, and you'll see how that's reflected in what I presented here. So, yeah. Java Performance Tuning. Actually, no, it's just Java Performance. I apologize. Yeah. But Charlie Hunt is the author, and Binu John as well. Wait, question over here?
Yeah, I have a question about survivors.
Okay.
After a situation in which either the survivor space shuts or it's not used at all. I watch the sign, it says 0, so...
Are you allocating very large objects? Okay, so it could be that adaptive sizing is enabled. So if you have to disable adaptive sizing. It's use adaptive sizing. If you disable that, then you should have direct control of your survivor spaces. There's two flags though. There's initial survivor space size and initial survivor ratio and survivor ratio, I believe. But there's one that's tricky. It's called target survivor ratio. You think, oh, that's the target. No, it's not. Actually, what that is the target capacity of your survivor spaces. So look that one up. I would avoid target survivor ratio unless you know exactly what you're doing. And if you understand it and it makes sense for you, then it's probably good to go. But you gotta understand what it does first, and the name is poor. So, yeah. Question here? Or? Okay.
You mentioned the measurement of the memory for regression tests or something like that. How do you trigger are you really sure that you're down to the steady state? Because in the system G, I see if I trigger it 3 times, it goes down a little bit more, something like that.
I mean, there is a notion of settling. Now, most likely what's going on in your application is that you're using like soft references or other references that need to resolve their... I mean, when you do a full garbage collection, if it has live objects that are pointing back to the young generation, and they may be dead, then those objects have to stay in the old generation until those objects in the young generation die. So sometimes there is some flux. So I would do, if you're using explicit GC, you probably have to do several in a row to make sure that those objects that are into the young generation, and if it's still a live load on the application, it can be influenced in that. So it's probably a rolling average you have to look for in that situation, because really the only way you're going to come to a steady state if you have cross dependencies across the generations is really stopping injection, like stopping work coming into the system, and then you can come to a steady state and know where you're at. But if you're not able to do that, then yeah, it's going to be a rolling average. So if it's regression testing and it's at a steady state, meaning are you still under load, or is it just? And then do several and see where it settles. That's what I would do. And the reason it takes a little while is because of the cost of that. Because of objects either being soft references and needing to resolve their references before they're collected, or they have other objects that point back to objects in the young generation that are still there. Yeah. All right.
Just another question. During our performance testing, we wanted to recreate certain things that we've seen in like the full GC.
Mm-hmm.
Sometimes you have to let it run for days.
Yep.
So is there any way to invoke a full GC?
Well, system.gc will invoke a full GC at that point in time. There's also a way of doing it in CMS. I don't remember the flag, but you can look up.
So if you were to use like the JMX.
Yeah, exactly. One thing you have to make sure is that, well, if you're doing CMS, there's flags that will set, maybe because you're using CMS, and if that's the case, then there's a flag that specifies whether it's explicit or not. And how does it interpret an explicit GC? I don't remember what that is. You can look that one up. But if you're using minus explicit GC flag, it will disable that invocation.
We got the GC, it just wasn't full.
Okay, then most likely it's CMS, and it's probably one of those flags. Yeah, you look control that. Yeah, exactly. If you take a look at if you just do Java minus XX colon plus print flags final, capital P, capital F, capital F. I think that's right. It basically dumps the state of all the flags, at the end of the invocation of your JVM. So you'll see everything that's set. Question?
I don't remember which of the examples, but one of them you had max new size and new size is 16.
Yeah, that was a mistake. That was a mistake. I tried. They should have been the same.
You never said it different.
Max new size and new size.
On that resizable shit.
No. Yeah. If you're doing that level of tuning that we're talking about here, no, never do that, because it's a waste of time. Yeah.
Is there a full GC when you change the new size? Like
No.
when you change the
No, it's only the generation that you're resizing is the generation that needs to invoke the GC. So young generation is pretty adaptable in that regard. So no, it doesn't. It's not necessary. Yeah.
That's only for the new size?
If you're running in a server application, I would set both the young generation and the old generation to fixed sizes. So there's no resizing in between. It's just unless you're the only, as I said in the presentation, the only situation where you'd set the maximum heap size and the initial heap size different is if that you're trying to over provision the system. If you're trying to run 96 gigs of heap, but you only have 64 gigs of actual memory, and you think you can get away with it, which you won't really. You might for a little while until something wakes up, but that's the only case I've seen people try to do that. Yeah. Yeah, exactly. On servers. Clients, that's a different situation. You don't want to only use what you need, right? So, question?
Are you able to keep it running with no full GC? Just steady state?
We avoid all full GCs. Yeah. Yep, that's how it works. Now, there's a lot to that, though. I mean, there's a lot of control on the change in code. So, yeah. Mm-hmm.
Do you have any recommendation on tuning a JVM that may be unrelated to, or identifying when an unrelated JVM is having a negative impact on it, like the problems coming in on JVM?
Okay, so right. So if you're running on a hypervisor with separate OS instances, and those OS instances have binded CPUs, meaning that they can't go beyond a certain set of CPUs that they're running on, I don't think there's a lot that really matters, because the JVM is only going to see what it sees within what the aspect of what the operating system has. I'm sorry? Oh, so if they're not binding it, then you probably want to limit the number of GC threads that are run. Yeah, I think that's probably the biggest thing that you can do. That being said, if you like in situations where like high frequency trading and you're trying to get sub-millisecond response times, a lot of time they run those systems at utilization rates that are like less than 5%, sometimes less than 10%. And the reason why they do that is if you're well below the curve of, basically response times will kind of chug along, increasing a little bit as you increase your CPU utilization. And then right around 60%, they start going up a lot. Sorry, banging the mic. But if you get down well below the knee in the curve, sometimes that tuning changes, because at that point, the ratio between mutator threads and CPU caches and what's available on the CPU is quite a bit different. So sometimes running more threads in that situation is better. But that's not, if you're running virtualized, you're trying to use the system more fully. So I think that's what you would do is clamp down the number of GC threads. Also, don't do flags like use NUMA at the same time, because it doesn't know enough to what's going on. If you're using C states, C sets or I'm forgetting the term. Yeah, that's right. And that's a little different, because that gives partial observability into the complete system. And in that case, you definitely have to tune your thread counts, because the JVM will just think it has all the threads that are on the system, and you'll have, you will be competing for CPU resource during garbage collections. So, okay, right here.
You mentioned the use NUMA effect. Can you talk about that and when it's recommended?
I would use NUMA when you're running on a NUMA system. First off, using parallel old garbage collection is the only one that really works with it right now. I think G1 will be soon. No, it's not default on.
Parallel old meaning not CMS or PARNU?
Not CMS or PARNU is the parallel young generation collector for CMS. Parallel old is just a throughput collector. It used to be just parallel GC. Parallel old is on by default. Is that what you meant? NUMA wouldn't be on by default because it ends up being counterintuitive if you're not running on a NUMA system. What it does is it chunks up the young generation into the CPU, the local CPU NUMA nodes, right? So if you're running on a four-way, you have four, regions of the young generation those threads those T-labs, which threads are allocating into, will stay local to those regions, right? So you have local allocation in young generation. But in the old generation, that doesn't really happen, and so we interleave across the nodes in the old generation. So the old generation is allocated, interleaved across the NUMA nodes, and the young generation is spread, across the NUMA nodes and allocated locally. The reason why we do that is that the heap is allocated at initialization of the JVM, and an operating system will always say, "Okay, I'm running on a NUMA system. You just, you're starting your thread, you're allocating memory. Let's put all that memory next to that starting thread." So if you don't use NUMA, or you don't interleave your memory on a NUMA system, your heap will be allocated on one NUMA node, most likely, and that depends on what the configuration of the operating system is. And then n-1. Well, basically, yeah. I'm not going to try to do the calculation quick on the fly here, but most of your memory accesses will be remote in that situation. So. Yep. And then every memory access is going across the memory bus.
If you spread it evenly, at least you can, on balance, be 50% of the time.
Exactly. That's the benefit.
If I'm using PARNU and CMS, what effect could NUMA have for me?
None. Doesn't do anything. The collector doesn't know how to do it.
But doesn't it impact the initial allocation?
No. It could. That's actually not a bad idea. Maybe they should do that, because then it would at least be interleaved, right? But no, it hasn't been. Oh, does use NUMA interleave the old generation if you're running CMS? That's not a bad idea, though, John. Okay, good. Excellent. John is one of the GC architects, so you can also ask him questions.
So maybe if I'm really latency sensitive, one extreme approach is to isolate CPU cores and only run on one socket, pretend the rest of the machine does this.
Yeah. Or isolating those, or the GC threads to a socket and your application threads to, and dividing it up that way.
You can do that?
Yeah. Well, you can't do it like manually. Can't do it on the command line, but you can do it by inspecting your threads and doing it that way. But that's really corner case stuff right there.
Order of magnitude kind of estimates for how much the NUMA penalty is for
newer systems right now, I'd say modern Intel processors on a two-way, less than 5%. It's really not that much on a two-way. 4%, you're getting close. A four-way, close to 15%. Yeah. As far as difference in overhead, yeah, it's that. You can.
talk about latency for a remote access.
Oh, yeah. You can do that just by doing numeric control minus show. I don't remember what it was. If you really look at the numeric control tools on Linux, it actually will give you a diagram of what a local access and what a remote access, what those timings are on that system. You're talking, probably a 5x magnitude difference between the two, which is not terrible when you're talking about a couple nanoseconds, frankly. So, but that's really from memory. I don't remember. I don't remember what they are. I look them up. Yeah. Any other questions?
Is that like modifying an existing PC or
Both. I mean, right now it's both. Yeah. I mean,
is it far along or is it just starting?
the effort's just starting. I mean, we've had designs that we've been considering for a while, but we've hired the critical mass at this point that we can actually start executing. So we're in good shape. I'm sorry?
And it's planned for the OpenJDK.
Yeah, it's OpenJDK, and we have every intention to work with John and his colleagues to get them all the stuff back. Yeah, totally. Question?
Warehouse or the GC logs and stuff. Like not for one virtual machine, but
So the question is like management of GC logs, and what do we do? Well, we have our own. What we do well, I mean, if you're going to post-process and try to like understand the state of an application over time, that's a big problem. It's a lot of data. There's various different ways to do it. Right now, the most common way I've seen is really only keeping a certain amount of days worth of data. And because for one, it gets unmanageable from a space point of view, but also from what do you do with all these GC logs and correlating and timing differences and so forth. I think there are some tools out there that manage that, but I'm not terribly familiar with it. I'd walk the floor and see if the guys that do system management and system management tools, I bet they would. Well, somebody's got a solution. Yeah. No. Question?
Is there any recommendation on testing your tuning flag outside production? If you have some critical system that you cannot, every time try changing settings and put the production load, how do you simulate the allocation properties and promotion of the system without actually running the whole system? Is there any ideas of that?
It is a difficult problem. Developing workloads that kind of model what happens in production can be a kind of a red herring path that you take, right? I mean, it's something because things could be so different in production, and sometimes standing up your production systems in something that would be actually equivalent is nearly impossible. So the success that I've seen is trying to get enough state of the application tied with the garbage collection logs and getting an idea of what may have happened. But there's a gap there, right? There's not a lot of profiling tools that give you easy full stack analysis. There's very little allocation profiling tools that I've seen be successful and accurate. There's BCI tools, sure, but which is bytecode instrumentation where you can target a little bit of code and find out what's going on. But yeah, there's gaps there. So there's not that's a big problem, and I think that's a problem space that we'll see start to see some activity in. But I don't have an answer for it.
So you use primarily listing, especially for CMS, and parallel is much easier. CMS, do you do that primarily in production?
Tuning on production? No. We try to I can't give it. Obviously, I can't tell you what we're exactly what we're doing, right? So, but it
Simulate it on try to simulate as closely as possible in
if you can find a way to non-disruptively do it in production, non-disruptively is the key point there, right? That would be perfect, right? Now that's the kicker. So I think that would be cool. I mean, that would be awesome if you could figure that one out. But so that's yeah. Yeah, there's a lot of folks out there that spend a lot of time doing that, trying to model applications correctly. Okay. Oh, I don't think we have anything else right now, so nobody yelled at me.
Answer real quick.